Welcome back to Software Engineering 2FA3, Discrete Mathematics with Applications 2. My name is Bill Farmer, and today, as part of the topic on predicate logic, we're going to talk about the semantics of our version of first-order logic, FOL. So we need to start first and talk about what is a first-order structure. So a first-order structure consists of a domain, D. So it's some non-empty set of values and some distinguished values, A1 through AN. And these distinguished values are of one of three kinds. Either one of these is a member of D, or one of these is a function that takes several arguments from D and gives back a value of D. Or it's a relation or predicate over D, which if it's a relation, it's going to be a subset of some Cartesian product of D. And if it's a predicate, it's going to be a function that takes several arguments of D and gives back the value false or true. So that's what a first-order structure is. There are many first-order structures that we run into in mathematics. I've given some examples here. I won't go in detail about all of them, but the first one is D is our set of natural numbers, and less than is either the relation or the predicate over D, the normal relation, which says that M is strictly less than N, where M and N are natural numbers. And then we have the semi-ring of natural numbers. This is the algebraic structure of natural number arithmetic. We have 0 and 1, plus and times. We have the ring of integers. By the way, these kind of names, ring, semi-ring, and ring, field, these are different kinds of algebraic first-order structures. Algebraic structures in this case are first order. So a ring of integers is the integers with 0, 1, plus negation and times. The field of rational numbers is irrational numbers with 0, 1, plus negation, times, and the inverse operation. And then I have two examples which are Boolean algebras. Boolean algebras are also algebraic first-order structures. The domain for a Boolean algebra truth values is this false and true, and then there's a 0 element which plays a role which is played by F, a 1 element played by T, and then we have an element here which is like the join of a lattice, and this is like the meet, and this is complement. And we also can have a Boolean algebra of sets where this is the power set of A, the set of all subsets of A, the empty set, the whole set, and then we have union, intersection, and set complement. And we get a different Boolean algebra of sets for every non-empty set A. Now, just for your own information, first-order structures are a special case of mathematical structures in general. A mathematical structure in general could have several non-empty domains, and it could have a bunch of distinguished values, but these values don't have to be of one of the three kinds here. They could be really unrestricted. They could be much more involved. So first-order structures are special kinds of mathematical structures. Mathematical structures are everywhere in mathematics, and some people have even gone as far as saying mathematics is really the study of mathematical structures to a large extent. So I've given some examples of mathematical structures. We have number systems. We just talked about some of those for natural numbers and rationals and reals. We have orders, like partial orders, total orders, equivalence relations. We've talked about these. There's algebraic structures. I've already mentioned some. semi-rings, rings, fields. Lattices, we sort of mentioned lattices because Boolean algebras are special kinds of lattices, and graphs and trees. Vector spaces. Vector spaces are interesting because there's two domains. There's a domain for vectors and a domain for scalars. Metric spaces, topological spaces, measure spaces. And then there's a whole bunch of mathematical structures that come from computing, and these correspond to various kinds of abstract data types like strings and lists, streams, arrays, records, stacks, queues, and so forth. Okay, so we know now what a first-order structure is. It's a special kind of mathematical structure. And what is special about it is it has only one domain, and its distinguished values are all of just three kinds: members of D, functions over D, relations or predicates over D. Now, as far as FOL is concerned, we will always be using predicates. So really, you can freely go back and forth between relations and predicates. But in FOL, we're going to think about relations as predicates. And just to remind you, a predicate is just a function that gives back false or true. Okay, so we're ready now to define the semantics for FOL. So this semantics will depend on a signature. So if we have a signature sigma, there will be certain terms and formulas of that signature, and we want to give all those terms and formulas a value. And the first step is to define something called a model. It is going to be a domain, a non-empty domain D, and an interpretation function. And this interpretation function is on the members of our signature, the constant symbols, function symbols, and predicate symbols. And this interpretation function follows these three rules. The interpretation of a constant is always a member of D. The interpretation of a constant symbol is always a member of D. The interpretation of a function symbol is going to be a function over D, and if the function symbol is n-ary, the function over D will be n-ary. And so the interpretation of an n-ary predicate symbol will be an n-ary predicate over D. A model of sigma is basically a way of interpreting the symbols of sigma as mathematical values. So when we think of these, C, F, and P, we don't think of these as values, functions, and predicates. They are symbols. This is a symbol, and by a model will tell us how we're going to interpret it. And F is a symbol, and the model will tell us how to interpret that. And P is a symbol, and the model will tell us how to interpret that. Now, if our signature has this form, in other words, it's finite, so basically this says this signature is finite, then we can form this tuple, which is D, the interpretation of all our constant symbols, the interpretation of all our function symbols. And guess what? This will be a first-order structure. So a model is really a domain, and it's an interpretation function, but the domain and interpretation function, they define a first-order structure. Okay, so let's move on. So let M be a model of D. Now, we would like to define the value with respect to this model for every term and formula. Now, we sort of have a problem. Let's say I had a term like x equals 2, where 2 is a constant symbol, x is a variable. What would the value of this be? Well, there's no real way of giving a value of this because we don't know the value of x. And x is a variable, so it could have many different values. So we have to have a way of giving a value to this by knowing what the value of x is. And we do this with something called a variable assignment. It's a function that maps each variable to an element of D. So this is a variable assignment into our model. So every variable gets mapped to some member of D. I wrote this as script D, but it's just a regular D. And let assign M be the set of all variable assignments. And now we have to have this little technical definition. If I have a variable assignment phi, so this maps every variable to a member of D, I may want to adjust it slightly. I may want to take some variable x and change its definition. Let's say x goes to some value. I want to change it to a different value. I'll call that value D. So what this equals, if I take this variable assignment and apply it to a variable y, it equals y, or I should say it equals phi of y if x does not equal y, and it equals D if x equals y. So this is a technical definition we're going to need in a moment. So now what I'm going to do is define a valuation function, which I denote like this. It's a function v, and I have this valuation function for a particular model, and that function is going to allow me to define a value for every term of sigma and every formula of sigma. And this will be a binary function. It will take one of these things we just defined up here, a variable assignment, and it will take either a term or it will take a formula. Now, it's convenient not to write it this way, but to write it this way and put the variable assignment here. But it's still a binary function. It takes two arguments, phi, the variable assignment and term, and phi and the formula. And here we have 8 parts of our definition. So this valuation function, it's going to satisfy all these conditions for all variable assignments, all terms t, and all terms 8. It's defined by pattern matching, and notice that we have 3 patterns for terms, and as you would expect, 5 patterns for formulas. And so this is a very important definition because it's basically telling us, once we have a model, how we can interpret every term and formula of sigma. Okay, so I'll go through this. So the valuation function tells us, in a sense, what these things mean in this model with respect to this variable assignment. So the meaning of x is just going to be whatever the variable assignment assigns to x. And the meaning of c, the value of c, is going to be whatever the interpretation function assigns to c. And the value of this function symbol application is going to be the interpretation of f, which is some function, applied to the values of t1 through tn. And if we jump to the predicate symbol, it's exactly the same. It's going to be the interpretation of the predicate applied to these. The only difference between these two is that the value of this is going to be a member of D. The value of this is going to be true or false. Okay, so the value of an equality is true if the value of S equals the value of T. Otherwise, it's false. The value of a negation is false if the value of A is true. Otherwise, it's true. The value of implication is false if the value of A is true and the value of B is false. Otherwise, it's true. So these are pretty straightforward. Once again, the universal quantifier is a little trickier because what we want to say is that the value of a universal statement like this, which says for all x, the value of A at x is true. We want to be able to say that. So we want to say that this is true precisely if the value of A is true when we adjust our valuation function so that x goes to d. So this is true if this is true for all d. So no matter how we interpret x, no matter what member of big D that we use to interpret x, the value of a will always be true. If that's the case, then the value of this thing is true. Otherwise, it's false. So if it was false, that would mean there's some d, there would be some d, such that when I use this variable assignment, that the value of a with this variable assignment will make this false. Okay. Now, we basically have defined everything, but to sort of understand how we use these notions, we have to add some more definitions. Okay, so let's say I have a formula A, I have a set of formulas gamma, and I have a model of sigma. So this formula is a formula of sigma, and gamma is a set of formulas of sigma. Okay, so we say that A is satisfiable if the value of A is true for some phi and some model. So if there's some model and there's some variable assignment into that model that makes A true, we call it satisfiable. So one way to think about this is a formula is satisfiable if there's some situation in which it might be true. If it's unsatisfiable, that would mean it is false in every situation. Okay, so let's move on. So A is valid in a model, and another way of saying that is M is a model for A, and we write it like this. If the value of A is true for all variable assignments in M. So this means that A is valid in a particular model if it doesn't matter what the values of the variables in A are, what the values of the free variables are. No matter what the values are, it's always true. So here's a simple example of something that would be valid in every model. So here we have a free variable x, but it doesn't matter. I should say this is going to be, the value of this is going to be true in every model for every variable assignment. Because if we're talking about the natural numbers, I assign x to be 1, basically I would be saying 1 equals 1. Or if I assign it to be 10, it's 10 equals 10. So that's what valid in a model means. And then there's another notion called universally valid, or sometimes people just call it valid, which we write like this. And that means it's valid in every model. So something that's universally valid is something that's going to be true in every situation. It is always true. Guess what? X equals x is an example of something that's universally valid. Okay, so we can also define a model for a set of formulas, which we write like this. Remember, this is how we write. M is a model for A, and here's M is a model for a set of formulas gamma. What that means is M is a model for B for all B in gamma. Okay, now we have one more definition, and this is in many ways the most important definition. It's the definition of semantic consequence, which is a special form of logical consequence. Remember I mentioned a while back that the key notion in logic is logical consequence. Here it is. We've defined our semantics. We're going to end with this notion, and we're going to let sigma or delta here be a set of sentences. And we will say that A is a semantic consequence of gamma, which we write like this. And I'll just say it in words. If every model of gamma is a model of A. So a model of gamma would be a model in which all the sentences of gamma are true. And if we have such a model in which all the sentences of gamma are true, then A must also be true if A is a semantic consequence of gamma. So another way of saying it, A is a semantic consequence of gamma if A is going to be true in every situation in which all the formulas of gamma are true. Now, notice that I said that gamma was a set of sentences. We can write as another definition that works if gamma is a set of formulas, but it's a bit more complicated, so I've decided to skip that. And usually when people talk about semantic consequence, most often they're talking about semantic consequence of a set of sentences. But there's another definition that works for formulas. Okay, so here's a question for you. Which of the following formulas is not valid in FOL? So remember, valid means it's basically going to be true. The value that's assigned to the formula will be true in every situation and for every model. That means every model and every variable assignment. Okay, so which is not valid? Well, we know that this is valid. I just mentioned that. This is also valid because no matter what value I assign to P and A, this is going to be true. Because if this is true, then this will be true. And if this is false, it doesn't matter, the whole thing will be true. Okay, this is also valid. There exists an X such that X equals X. Now you may say, well, why is that true? Well, that is true because of one of our conditions about models. The domain here, D, is a non-empty domain. Remember, a domain is just a set. It's non-empty. It has to have a value. Therefore, this is valid. This is a valid sentence. This will always be true. It will be true in every model with every variable assignment. So that leaves D. D says there exists X and Y such that values of X and Y are not true. This is not valid. Remember, we're looking for not valid. This is not valid, and the reason this is not valid is that we could have models where D has one value. It's a singleton. This says that this formula is only going to be valid when our domain has more than one value. Okay, so let's talk a little bit about quantifiers. Remember, in FOL we have basically one binder, which is the universal quantifier, but we have introduced another one, existential quantification, by a notational definition. So when we write this, we really mean this. So whenever we write this, we really mean this. That's what a notational definition is. You can think of it as a kind of abbreviation. This abbreviates this. But notational definitions they're not always abbreviations, but usually they are. Okay, so we can think of universal and existential quantifications, they're duals of each other. It's something similar to the De Morgan laws. Remember the De Morgan laws where if I had the negation of A or B, that's equivalent to the negation of A, and then I flip this and the negation of B. So it's something similar here. When I take the negation of this, I flip this and get this and the negation of A. In the same way here, when I take the negation of an existential quantification, I flip E to A. I flip backwards E to upside down A. Okay, so the universal quantifier and the existential quantifier are duals of each other. Now, another thing I want to mention is that changing the order of quantifiers is usually changes the meaning of the formula. So if I have for all x there exists y(a), that is not always equivalent to there exists y such for all xa. So I'll let you think about that, come up with some examples of why that's true. Now, in a formula of this form, for all x there exists y(a), the value of the existentially quantified variable depends on the value of the universally quantified variable. So this says, for all x there exists a y such that these x and y satisfy a. But for different x's, I may need to get different y's. Now, remember in FOL, we have just one domain of individuals, and we don't have multiple domains. So if we make a statement like all mice are rodents, we have really two kinds of things here. And so if we were going to write this in FOL, we would write it as for all x. So for all x means for all the things that we can talk about, all individuals, if that thing is a mouse, then that thing will be a rodent. So this is a fundamental way how we express a universal statement like this in FOL. And if we have an existential statement like some rodents are mice, we would express that like by saying there exists an x that is a rodent and a mouse. Now the one thing to notice here is that when I did this conversion, here I needed an implication, here I needed a conjunction. So with a universal statement of this form, if you're going to turn it into for all x ranging over all the individuals, we got to put an implication here. Here in this case, we have to put a conjunction. Okay, so that ends our discussion on the semantics. Of course, much of this probably you haven't fully understood. The way to understand this is to do exercises. Doing exercises will force you to work through these definitions, and you will come to a deeper understanding what the semantics is all about. Okay, so next time we're going to be talking about FOL theories. So, see you then.